90 million miles from Earth. Faster than anything ever made, a spacecraft plunges into our sun. This tiny craft, no bigger than a car, faces a star 1,000,000 times the size of our planet. Once considered mission impossible, the probe needs cutting-edge new technology to survive. Its mission, to solve the mysteries of our awesome star.
It's the first time we've ever gone this close to the sun. It's been an engineering feat to actually get there and not melt.
New data will help warn of the dangers of electromagnetic explosions from the sun.
Solar storms can cause blackouts over large parts of the world.
Nothing from Earth has ever been this close to our star before.
It is uncharted territory, and Parker Solar Probe is blazing her way through there.
It's a mission 60 years in the making. Finally, we are touching the sun. Cape Canaveral, Florida. NASA is going where no mission has gone before. They're heading to the sun.
The rocket has been at the launch pad awaiting the arrival of Parker's Solar Probe. She's buttoned up, looking beautiful, ready to go.
In charge of the science for the $1.5 billion mission is project scientist Nikki Fox.
The mission is inspiring. It is a voyage of discovery. We're going to the last region of the solar system, really to be explored by a spacecraft. It's like discovering a new continent. We've sent spacecraft to all of the major regions of our solar system.
That's one small step for man, one giant leap for mankind.
But we've never gone into the center of the solar system. It is uncharted territory. So there is a lot of pressure to be perfect for that 5, 4, 3, 2, 1 liftoff moment.
The Delta IV Heavy, America's largest rocket, launches 50,000-pound spy satellites into orbit around the Earth. The tiny Parker Solar Probe weighs only 1,500 pounds. But it needs the power of this rocket to gain the speed necessary to travel the 90 million miles to its target, our sun. The sun sustains all life on Earth. The whole solar system created by its massive presence. You could line up 109 Earths across the face of the sun and pack over 1 million Earths inside it. It's so large, it would take a jet plane nearly 6 months to circumnavigate the sun. At its heart, a giant nuclear fusion reactor, crushing atoms together and generating 27 million degree temperatures. Around that, a vast ball of superheated plasma, an electrically charged cloud created when atoms are torn apart by heat and pressure beyond our understanding. This awesome power of the sun constantly changes, which is why it's studied 24/7 here at NASA's Goddard Space Weather Research Center. Real images of the sun like these are filmed by NASA's solar observatories in orbit around the Earth.
When you
step outside of the atmosphere with a camera in space, we find the sun is so much more interesting. It's this explosive environment that is seething with energy. Magnetic and electric fields are moving around. It's ever changing. This is what's so amazing, is to see how incredibly dynamic the sun is.
Dynamic and racked with gigantic explosions, hurling radiation and particles towards the Earth.
You see lots of little flashes. These little things are many times the size of the United States, for example. They're huge, and they're massive amounts of energy being released. It's mind-boggling. All that dynamic energy can occasionally throw out these huge solar storms, these blasts of material that can slam into the Earth. They shake the Earth's magnetic field. So this is one of the reasons why we focus so much on what's happening on the sun.
On Earth, we're blissfully unaware of these massive explosions millions of miles away in space. Few people alive today have ever felt the impact of a major eruption on the sun. But 159 years ago, the biggest sun explosion we have ever known causes chaos on Earth. September 1st, 1859. English astronomer Richard Carrington draws images of sunspots projected through a telescope at his home in the English village of Red Hill.
All around the world back then, people were watching the surface of the sun. And every day, Carrington would sit down in his observatory, which was a telescope he had in his house, and he would look at the sun and project the sun down, and he'd make a sketch of this active region. By cosmic coincidence, as he was sitting there making a sketch one day, one of the largest solar flares on record occurred. Carrington was actually able to see bright pricks of light appear on his sketch pad because the flare was so intense and visible light, it actually caused bright points to appear on the solar surface.
Carrington's drawing records the largest flare ever known since then. It's the first indication for scientists that storms in the sun can devastate our technology on Earth.
What's amazing is then what follows. About 18 hours later, all hell breaks loose on Earth. Telegraph lines start sparking and catching on fire. Compasses start wiggling around.
It was enormous. It was so big, it made what we call a geomagnetic storm, which is one of these storms where it deforms Earth's magnetic field and puts all of this energy into the radiation belts.
The aurora borealis, the northern lights, are seen all the way down to Cuba.
Places of the world where people had never seen aurora before. Places like Australia, Great Britain, and even Florida could have seen the aurora.
The geomagnetic storm that spreads chaos across the globe is now known by scientists as the Carrington event. In 1859, the newly invented telegraph machine is the only method of long-distance communication. Electromagnetic particles bombarding Earth from the huge solar flare have serious consequences, wrecking communications.
So in 1859, the loss of the telegraph system for 4 days, that doesn't seem that significant when we think about that today. But if you imagine the loss of all electronic communication, all power grids for days, weeks, months, it is a huge, huge impact on life and society.
Some estimates say that if it were to happen today, and we didn't have enough advanced warning to power down our power grids, you could lose all the transformers on the east and west coast of the United States. It could take years, maybe even decades, to restore power to the coasts.
Imagine losing the internet now. National panic would ensue.
You lose GPS potentially. A lot of us depend on GPS for things like logistics. Most major cities in the world only have enough food for about 12 hours. So if you don't have a logistics network, operating, you can't supply all the people in the city. When a hurricane strikes, if there's an earthquake, what do? People leave the city, they take refuge in another city nearby. You don't necessarily have that option if we have a Earth-level Carrington event. If you lose the entire seaboard, there's nowhere to go to recover.
No one knows when a Carrington-level event will happen again. It could happen right now.
So imagine now, if we had one of those major events, it would be pretty bad. So we need to mitigate the effects of this.
Reducing the effects requires earlier warnings of solar bombardments. And for that, we need scientific data we can only get by going to the sun. So, that's what we're doing.
10, 9, 8, 7, 6, 5, 4, 3, 2.
August 12th, 2018. In the early hours of the morning, Parker Solar Probe is ready for liftoff.
There's a tremendous amount of excitement in the team waiting for this launch. We are so connected with this spacecraft. We've watched her grow up in front of us for many years. To us, she's a person, she's a part of the team. She is the one that's going on the voyage and going to make these amazing discoveries.
Status check to proceed with terminal count. First station, propulsion. Go. Hydraulics. Go. Locks. Go. LH2.
Launch is probably the most dangerous part of the mission. You're sitting on top of a tremendous set of tanks of explosives. Is a controlled explosion. If you lose control in the slightest way, that's it. It's all over.
9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Liftoff of the mighty Delta IV Heavy rocket with NASA's Parker Solar Probe, a daring mission to shed light on the mysteries of our closest star, the Sun.
It was just like she was ready to go. And so I think for the first time in months, I was actually speechless watching that beautiful sight of her lighting up the sky.
Tower clear. Now 10 seconds into flight.
Even though we're a few miles away from the rocket, the noise from the launch is so intense, you can feel it rattling in your chest.
Those two side boosters are going at full throttle. As they start to burn out, they drop away, and the center one takes over as the main lift body.
92 miles above the Caribbean, the nose cone splits apart. Scientists and engineers in 4 different mission control rooms around the country follow every second of the Parker probe's progress. 30 minutes later, the second stage separates. The Parker probe is finally leaving the Earth.
There are so many different feelings kind of jumbled up in my head at the same time. The pride, the sheer spectacle, but also separation anxiety. That's my baby, and she's left the planet. I hope she writes every day and tells us all the wonderful data she's taking.
The Parker probe's mission will last 7 years, one of the most complex navigational challenges ever undertaken in space. 24 orbits, each one taking the probe closer and closer to the corona of our star. But this route has a crucial first step, a flyby of Venus, using the planet's gravity to turn Parker towards the sun. There's little room for error. To aim at Venus, the probe must fire its last engine precisely on time.
That's when we get most of the speed, and if we miss Venus, it'll destroy the entire mission. We won't get the orbit that we want. Except Venus is a moving target. And so we can't aim at where Venus is, we have to aim at where Venus is going to be in weeks when we finally get there. So it's sort of like a sniper. If you had a sniper aiming at a target that was 1,000 yards away, he'd have to aim very precisely to hit that target.
But Venus is a moving target, and that comes with its own set of problems.
A bullet travels at about 2,000 feet per second. So it takes almost 2 seconds to travel that 1,000 yards.
The sniper would need to aim at the exact point where the target will be 2 seconds into the future. Even for a mere 1,000 yards, the calculations need to be precise. Over 32 million miles, and at 50 times the speed of a bullet, the team at NASA has an even more difficult task on their hands. To aim in the right direction, the probe has one last engine on the third stage of the rocket, and it should be firing right now.
The third stage is a solid rocket motor that fires once and then it's done. And so we've got to get it right. We've only got one opportunity.
Mission Control follows every moment of the flight by receiving telemetry from the probe. But there's a problem.
Seeing some telemetry dropouts from the third stage. Should have expected to see spacecraft separation within the last minute.
Telemetry from the spacecraft, its only means of communicating with Mission Control, has failed. There's nothing they can do but wait. No one is sure if NASA's Parker Solar Probe is in trouble or not, because it's not talking to Mission Control.
Seeing some telemetry dropouts from the third stage.
Telemetry, the readings its instruments should be transmitting to Earth, are failing to reach Mission Control. For scientists and engineers desperate to confirm that the final rocket burn has happened, frustration.
Should have expected to see spacecraft separation within the last minute. Difficult to make calls.
All everyone on the ground can see is a NASA live television feed, a pre-prepared animation of what should be happening in space. With no confirmation, this NASA picture could be just an expensive cartoon. And if something's wrong, there's no way of fixing it.
This is not the Hubble Space Telescope. Whatever happens after launch, that's it.
If it's a serious error, the mission will fail. But moments later,
And we've been informed that the third stage is providing data to a ground station.
telemetry is reacquired. The Parker probe signal is being picked up by a receiving station, confirming the final burn.
We have had confirmation of spacecraft separation.
With the final engine separated, Parker probe is now safely en route to Venus. This voyage to the sun was at the top of the wish list of space exploration, drawn up when NASA was created in the 1950s.
10, 9, 8.
Other missions to Mars, Saturn, even Pluto have been successful. Only the Sun remains so unexplored. Their final frontier. The importance of visiting the Sun is highlighted back then by a young scientist, Dr. Eugene Parker. He discovers the solar wind, streams of electrically charged nuclear particles blasting out from the Sun in all directions. Parker's mathematical theory shows that the wind envelops the Earth, a potentially fatal danger to astronauts outside our planet's protective shield.
Depressed in the surface about 1 or 2 inches.
Back in the 50s, Parker's ideas are so revolutionary, many don't believe him.
I remember how upset some people were. They insisted I made a mathematical error, and I would reply, well, here you are. Here's 5 lines of algebra. You say I made a mistake. Show me.
The danger Parker discovered grows even greater when solar flares or other eruptions increase the blast of deadly radiation. Astronauts landing on the moon were at risk, but they were exposed for just a few days.
Although the surface appears to be...
Now, manned missions to Mars are high on NASA's agenda.
Very fine-grained as you get...
Even inside their spaceships, future travelers to Mars run the risk of radiation poisoning.
-15.
NASA realizes we must go to the Sun. But for 50 years, they just can't do it.
At first, the findings were, it's impossible. Can't be done. We just don't have the technology. It would melt. We couldn't get there. Finally, in the mid-2000s, all this technology came together, and we figured out that we could actually build a solar probe and fly it.
It's not surprising that for so long, reaching the Sun is considered mission impossible. We view our star with awe and reverence. To us, it's a solid presence in our sky, but in reality, there is no solid surface. Just plasma, countless beams of light bursting out from its nuclear core. Above is the Sun's atmosphere, the corona, a shimmering cloud only seen as a ring around the Sun when there's a total eclipse. Or in images like these taken by NASA's specialized telescopes. Within that corona is a scientific mystery, which Parker Probe may help to explain. The corona's outer edges, furthest from the heat of the nuclear core, are hotter than the surface of the Sun, which defies the known laws of physics.
The visible surface that we're used to, that yellow ball, is about 6,000–7,000 degrees centigrade. But when you move away from the surface of the Sun into the outer atmosphere, what we call the corona, it's actually millions of degrees. It's crazy. You can think about, if I step away from a campfire, it gets colder as I walk away, but the Sun doesn't do that.
Instead, when your campfire is the Sun, step away from the heat and you get hotter than ever before. In order to solve that mystery and discover how the furnace heat of the Sun powers dangerous rays towards us, the Parker Probe must reach its target. The spacecraft is packed with a vast array of scientific instruments. The only question now, can the Parker Probe deliver them safely to where they need to go? Parker Solar Probe is hurtling towards Venus at an astonishing 68,000 miles an hour. Drive that fast, and coast to coast across America is easy. New York to LA in around 2.5 minutes. And as the speed increases, they need to make make sure their instruments are working.
If something goes wrong, it probably went wrong during launch. You know, something shorted, something shifted, something broke.
Unlike your iPhone or your computer, if there's a problem, you cannot, walk down the street and get it fixed.
One by one, the systems switch on and send back data. The process takes weeks. There's a lot to check.
Parker Solar Probe is about the size of a car, but there are a tremendous number of components jammed into that.
Antenna capture data about magnetic fields. The only camera on board photographs the solar wind rushing by. Analyzers capture high-speed particles as they accelerate into space. But only one instrument has the power to withstand the full fury of the sun.
The bravest little instrument on the spacecraft, the Solar Probe Cup. It is out, it's looking in the full solar environment, and it is measuring what is coming literally smashing into the spacecraft from the sun.
Particles from the sun pour into the solar cup and are funneled into detectors measuring their speed and temperature. The cup is the creation of solar scientist Justin Casper.
The sun's actually going to be 400 to 500 times brighter at closest approach than it is at Earth. So any exposed surfaces, like the front of the Solar Probe Cup, are going to get up to temperatures of maybe 1,500, 1,600 degrees Celsius. And unfortunately, I want the solar wind to flow into the instrument, so I don't get to put a cover over it to protect the hardware, right? I have to have it wide open and staring at the sun.
Building robotic instruments for space exploration has been his life's work.
Hey, all right.
3, 2, 1. We have ignition.
I was a small child as the space shuttle program was getting off the ground.
We have ignition of the solid rocket booster and liftoff.
In the 4th grade, I and pretty much every other student in the United States, we assembled in our cafeterias to watch the live broadcast. Sorry, just a sec.
T-minus 15 seconds.
Well, you can see this really impacted me.
T-minus 10.
We're all going to watch Challenger take off.
And liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
This was the first time a non-astronaut, actually a teacher, was going to fly up into space. And as you may know, about 60 seconds into the launch, disaster.
1 minute 15 seconds, velocity 2,900 feet per second out.
And we're all sitting there in this cafeteria, just what's going on? And that really changed me, that one moment.
Casper resolves to explore space, but in a way that minimizes the risk to human life.
Obviously a major malfunction.
I was just so struck at how willing these people were to take this risk to get into space. I wanted us to continue that, but I felt like for some of the riskier things we do, we should do this with robots. So I became deeply interested and passionate in robotic space exploration. I wanted to be part of that.
Casper works on a solar cup design for more than 10 years. He thinks that alloys of highly heat-resistant metals, such as titanium, zirconium, molybdenum, and tungsten, might resist the heat of the sun. But he doesn't have anywhere with enough sunlight to test that theory.
I was lamenting to a French colleague of mine that I had this, what I thought was a great idea for an instrument, but I didn't feel like I could really convince NASA it would work unless I hit it with all this sunlight. How am I going to do that?
The answer to Dr. Casper's question was hiding in rural France. In the Pyrenees mountain range, there's a scientific facility that's exactly what he needs. The thousands of mirrors of the solar furnace reflect and direct the sun's heat and light to one parabolic mirror, the height of a 13-story building, and onto one single point of focus. The lab's deputy director, Marianne Bellade-Pichon, tests raw materials in the sun's focused heat.
All the light is concentrated, and you will see the focus by using some water. In order to see that the solar flux is very high, we will burn immediately the wood. So I put at the focus, and immediately you can see it burns. At the focus, we can go up to 3,500 Celsius.
That's 3 times as hot as most volcanic lava, more than hot enough to melt a steel bar. Tests here convince NASA the Casper Solar Cup, made with heat-resistant tungsten, will survive the heat of the sun.
Amazingly, our colleagues in France helped us do all that testing, and that's how we were able to go from a simple concept to the Solar Probe Cup.
In mission control, early checks of the cup and other instruments on board show that everything has survived the launch. It's a big step towards mission success, but now there's another hurdle looming.
As we fly past the planet Venus, we will be eclipsed from the spacecraft. So there will be a short period of time where we can't hear from the spacecraft, and we just have to wait for her to pop out from the other side of Venus.
Every time you can't hear from it, I mean, it's like a parent who's worried about their kid, you know, who hasn't called. You would prefer to be in contact all the time. You can't, especially with this mission, which is flying to places where it's just impossible to get radio communications.
The probe is reaching Venus. It will soon be out of radio contact. When it reappears, the entire mission depends on one thing. It must hit its precise trajectory to the sun. The Parker Solar Probe has been out of contact behind Venus. This far from Earth, Mission Control has no way of affecting its destiny. As it finally reemerges, it beams back data showing its navigation is perfect. It's on course for the sun.
At some point when you get close to the sun, you can no longer talk to the spacecraft. The sun is a wideband radio source, which means it broadcasts very loudly on all frequencies, will drown out the spacecraft. So the spacecraft's on its own.
From here on in, the solar winds get stronger, and the danger increases.
She really has to look after herself on orbit. It takes light about 8 minutes to travel from the sun to the Earth. And so you can't joystick this mission. If the spacecraft has a problem, she has to be able to fix that problem herself.
But on Earth, these hazards are being closely monitored. Just like meteorologists who warn of storms and hurricanes, NASA scientists forecast the space weather the sun generates throughout the solar system. Their forecasts reveal what dangers the sun is sending Parker's way.
We actually do the space weather forecasting primarily because we want to protect NASA robotic missions. Space weather can cause different damages to instrumentation. It can actually fry them up and cause them to pretty much be trash.
Forecast teams like this not only warn missions like Parker of the dangers from the sun, but also warn astronauts like those on the International Space Station.
This is radiation, right? It can harm the astronaut, the person, if it's not blocked in some way. It has to have some kind of protection. Here on Earth, we are all protected because we have the magnetic field of the Earth. Outside in space, that doesn't happen. Having a mission that is going to the solar corona is going to help us understand this kind of activity in a better way. It's going to give us the data that we need to actually plug it into the models that we use for predictions so we can do better forecasting.
Nearing the heat of a star, Parker's survival now depends on one thing: its 5-inch thick heat shield.
The very first feature that jumps out at you is our heat shield. It is very critical for us. It is the thing that provides the shade and keeps the main body of the spacecraft cool. So it's highly important.
This all-important heat shield is the product of 10 years of work by engineer Betsy Congdon.
Betsy is an absolute rock star, and for over a decade, she has devoted her entire life to making sure that our heat shield works. She lovingly calls it her 8-foot frisbee.
At this approach, we're starting to get hot, and so the heat shield has to remain between the spacecraft and the shield at all times, so that the shield is protecting the spacecraft from the sun. It's basically a sun umbrella. In true engineering terms, the heat shield is surprisingly simple.
Behind the shield's reflective ceramic coating are layers of an engineered carbon composite. A shield so effective, it keeps the probe's important instruments at their normal working temperature.
Our heat shield will experience temperatures of up to 1400 degrees Celsius. It provides such an effective shade that the main body of the spacecraft itself is at about 30 degrees centigrade, which is a lovely summer's day.
With no guidance from Earth, tiny sensors behind the heat shield make sure it constantly adjusts to hide the craft from the searing heat. Sunlight hitting any sensor triggers an immediate response.
The spacecraft knows, oh, I might be skewing a little bit the wrong way, and so it actually will right itself without any human in the loop. So an autonomous system, which basically is, it's just working without us having to do anything. It knows what it needs to do, and it rights itself.
Adjusting itself is something the probe is going to have to do for the next 7 years as it swoops around the sun time after time. This vital system is about to have its first real live test. Temperature is rising. The probe is reaching the sun. The Parker Solar Probe has traveled a roundabout route to the sun. From its launch in Florida, it has journeyed millions of miles to Venus and millions of miles more to brush the atmosphere of a star. The hope now is that data gathered by its different suites of instruments, packed into every nook and cranny of the tiny spacecraft, will finally help solve the greatest mysteries of the sun. Flying through the plasma clouds of the sun's corona will let us better forecast the potentially dangerous space weather that can bring chaos to our modern society. In the future, what we learn today about our sun will guide our continuing search for life elsewhere in the universe.
Understanding the habitability of planets as we're seeing more and more planets in the universe is really important. We know that we have life on Earth because of the sun. We're in what's called the habitable zone. We're far enough away from the sun that we're not too hot, near enough that there's liquid water here.
The sun is our star. It gives us light, it gives us heat. We wouldn't be here without our star. But it is just an average star. The same as many other stars in many other solar systems. And so by studying our sun, it actually gives us insights into how stars all over the galaxy will actually work.
November 1st, 2018. Parker Solar Probe hits 179,000 miles an hour. It is now the fastest object ever made by humankind.
It's getting into the region where the solar wind is still being accelerated and where the corona is still being heated. That's what we mean by touch the sun.
Being this close to a star is like driving your car into the heart of a nuclear reactor. Nothing made by man has ever attempted such dangers before.
It's incredibly hot. The energetic particles are going to be very extreme, incredibly hostile place.
The heat is tremendous. The temperatures on the front face of our carbon heat shield are up over 1,000 degrees. All of our instruments hide in the shadows. They're still working. The science, the technology that's gone into getting us there has been tremendous.
On Earth, we think of light as pure weightless illumination. This close to the sun, light hits you like a hammer blow. The sheer pressure of the photons of light, its individual packets of energy, pushes the probe with a physical force.
Everything that controls our solar system is really from the sun. Energetic particles, the light, the solar wind, it all comes from the sun. To actually get to touch it is really amazing.
This is the beginning of rewriting the science textbooks.
We've successfully designed a spacecraft that can survive plunging into the sun's atmosphere, and that's an incredible accomplishment.
This is the moment we've been working for hard all these years.
Many, many hours, many gray hairs, and no gray hairs when I started this mission.
It's not the end of the mission, but on November 5th, 2018, at 10:27 p.m. Eastern Standard Time, the Parker probe reaches its first destination, a milestone in the human exploration of space. This is perihelion, the closest humankind has ever been to a star.
To be flying through the corona for the very first time is just incredible. It is uncharted territory, and Parker Solar Probe is blazing her way through that.
It's an alien landscape where magnetic tornadoes twist upward tens of thousands of miles. Mysterious dark spots, large enough to engulf the Earth, ebb and flow. And violent eruptions shoot tons of charged particles into space at speeds of over 2 million miles per hour. This is not some strange world on the other side of the galaxy. This is our sun. And now, new technologies are allowing us to see it like never before. The team at the National Space Weather Prediction Center begin their day as they usually do, carefully watching the surface of the sun.
Okay, a 10 centimeter came in today.
Although 93 million miles away, forces here can impact Earth in surprising and destructive ways.
The smaller.
The M6.
For the M6, you see this. The very first one is the M6.
Today, after years of relative calm, a satellite detects something. A dramatic explosion on the sun's surface. A violent solar storm that would dwarf Earth is erupting. releasing a massive shockwave, hurtling towards us at over 1 million miles an hour. Right now, no one is sure what to expect.
But I think that the M6 is going to get...
The team models the approaching storm.
Oh, 15Z for the arrival of the CME. This is it here.
Right
okay.
there.
Their simulation shows it racing out from the sun on the left towards the small dot on the right, Earth. The solar storm carries a 1-2 punch. First is a solar flare, releasing an outburst of X-rays that can reach Earth within minutes. The second, more ominous threat arrives a few days later, a phenomenon called a coronal mass ejection, or CME. It's a wave of billions of tons of electrically charged particles, seen here in this repeating image as it ripples away from the eye of the storm. Together, they could hit like a cosmic tsunami. Delivering a surge of radiation and an electrical spike of trillions of watts, potentially crashing the power grid. Sound far-fetched? In March 1989, in Quebec, Canada, that's exactly what happens. One by one, power stations crash, disabled by the overwhelming power surge caused by a CME wave. In less than 2 minutes, 6 million people are left without power. Recently, NASA's Jim Green finds evidence that an even bigger solar storm hit Earth in 1859.
And what we found was the granddaddy of geomagnetic storms, and that was just 150 years ago.
If we had a geomagnetic storm of that intensity today, the National Academy suggested that the impact on critical infrastructure could be catastrophic. And the big concern is the electric power grid.
The massive electrical surge from a CME wave could overload power lines and melt transformers, blacking out entire cities.
Repair could take weeks, months, and even in a worst-case scenario, the National Academy suggested up to 10 years for a full recovery.
If that occurred, if you can imagine a world without electricity, you're really going back in time.
It's not just the power grid that's at risk.
More and more, we rely on technology that could be affected by the sun. Global positioning satellites, long-distance communications, airplane tracking, astronauts in space.
Roger, how does it look?
So there's an urgency in understanding what it is that the sun is doing, what's it going to do next, and how can we prepare for that and respond to it.
Worried or not worried?
Well, I would be just a little bit worried, given concern right now. We'll be watching and monitoring it very closely here in the coming days.
We've gazed at the sun since antiquity. We've worshipped it and built entire cultures around its power. We marveled when it's eclipsed during the day. And when its power lights up the night sky with dancing curtains of light, the aurora. Its power and size are awesome. It is so huge, 1 million Earths could fit inside it. Temperatures at its core soar to 27 million degrees Fahrenheit. It's been shining for over 4 billion years, and will do so for at least 4 billion more. Yet for something that has such an overwhelming influence on our lives, the sun is mysterious. How does the energy generated in its core reach us as sunlight? What processes are at work inside the sun? How do these powerful inner workings generate explosive solar storms? The key to that explosive behavior lies deep beneath the sun's blinding surface. Until recently, seeing inside the sun was impossible. Understanding its internal processes, a pipe dream. But an accidental discovery changes everything.
Until the 1960s, much of solar physics relied on things that were like solar dermatology. It was things that were right at the surface or just skin deep.
But as physicists study the sun in more detail, they make a surprising discovery. The surface seems to be vibrating, like ripples on a pond. Initially, they think the vibrations are the result of defective instruments.
They couldn't get rid of them. They built better instruments, the ripples were still there. They looked at it for 10 years, and they conferences, they all talked about it, and they harumphed. But what it turned out to be was just sound waves.
It is an astonishing revelation. No one expects that the sun can generate sound waves. It leads scientists to see the sun in a completely new way. Our sun vibrates like a giant pipe organ. But instead of air producing the notes, churning gases deep inside send sound waves rippling through its interior.
Because a sound wave changes as it moves through different material, we can look at the different frequencies and determine what's happening inside the sun.
It is a powerful tool to see beneath the sun's surface. Studying the sun's sound waves reveals a complex, multi-layered machine. Directly beneath its blazing surface is a zone of perpetual churning. Next is a layer where light takes thousands of years to cross. At the center is the sun's core. It's the smallest region, but it's over 25 times the diameter of Earth. This is the powerhouse of our star. Everything we experience on Earth, sunlight, heat, and the effects of solar storms, starts here. So what's it like here? What's the core made of?
Well, the sun's a crazy place, right? It's far too hot to be a solid. We know that. Right? Heat it up, it's far too hot to be a liquid. And so you think, well, it's a gas, right? Well, not really. It is this gaseous soup of charged particles that we call plasma.
You're more familiar with this soup than you might think.
There are plenty of examples. Fluorescent light bulbs, flames, neon lights.
But plasma is radically hotter at the sun's core. The closest thing on Earth is lightning. During thunderstorms, electric charges build up, creating lightning bolts that reach tens of thousands of degrees.
That's pretty hot, but it's nowhere near as hot as in the core of the sun. So if you were to travel into the core of the sun, the plasma would be 15 million degrees.
As the sun formed, hydrogen gas at its heart was crushed under the weight of the material above. Eventually, temperature and pressure rose so high, the hydrogen atoms broke apart into electrons and protons, creating plasma.
And it's under these extreme conditions that something really, really cool happens. Nuclear fusion.
It's the same atomic process inside the hydrogen bomb. Under tremendous pressure, protons in the plasma fuse together, releasing photons, minuscule packets of heat and light. An unimaginable number of photons are made every second, generating the sun's incredible power, some of which reaches us as sunlight. This atomic alchemy converts over 4 million tons of mass into energy every second in an endless loop.
That much mass into energy is the equivalent of 10 billion hydrogen bombs being created every second. The sun does this day in, day out. It's been doing it for 4 billion years, and it's going to continue to do so long after I'm gone.
The force of billions of bombs is detonating in the core every second. This begs a simple question.
So you could ask, well, why doesn't the sun blow itself apart? It's because there's this beautiful balancing act that occurs. In the core of the sun, you've got this pressure from all of this fusion pushing outwards. And the sun is huge, so you have all this gravitational pressure pushing downwards. And so you've got gravity pushing down, and the sun trying to blow itself apart from the inside, and it is this beautiful balancing act between the two that keeps the sun in one piece.
This light, born at the core, reaches us after a remarkable journey. Away from the core, pressure and temperatures drop, and nuclear fusion stops. Now, each photon begins a tedious journey through the sun's thickest layer of plasma, a region called the radiative zone. Although squeezed less than at the sun's center, the plasma is still very dense, and photons struggle to move through it. Each packet of energy is continuously absorbed, then spat out by the plasma particles. Though moving at the speed of light, 186,000 miles a second, it takes photons over 100,000 years to cross the zone. Eventually, the photons reach a boundary where pressures drop again. The plasma thins, and moving through it gets easier. The photons still pack a lot of energy. Now, they leak out into the convection zone, heating it from below. These incredible images reveal convection at the sun's surface, rising and sinking plasma that creates a mesmerizing structure called granulation. Photons produced at the core finally reach the surface. they emerge as a weakened form of solar energy. This weakened energy reaches Earth in 8 minutes. We know it as sunlight.
So 100,000 years, about a month, and then 8 minutes. Once you get to the surface of the sun, it just takes 8 minutes to get to where you can see it.
Unimpeded, the trip from the core to the surface would take the photons a matter of seconds. In reality, the sunlight that shines on us today may have been created during the last ice age. Energy reaching the sun's surface doesn't just result in sunlight. It can also trigger solar storms. Understanding the sun's destructive power requires 24-hour precision surveillance, something that, until recently, was impossible to achieve.
5, 4, go for main engine start. 3, 2, 1, 0. And ignition and liftoff of the Atlas V with the Solar Dynamics Observatory.
February 2010. NASA launches its most sophisticated solar satellite yet. The Solar Dynamics Observatory, or SDO for short.
Coming up on Mach 1.
SDO is the first satellite to deliver almost continuous, super high resolution coverage of our nearest star, giving researchers unprecedented access to the sun and its secrets.
The first day was very exciting. We knew we were gonna open our doors to actually let the sunlight into the instrument for the first time.
We started looking at the first pictures, and it was almost in focus. And as soon as we focused it, it was just beautiful.
The new images reveal the sun like never before. An alien landscape where strange structures ebb and flow. Giant tornadoes, hundreds of thousands of miles high, that could easily engulf the Earth. And superheated bubbles of plasma the size of Alaska.
When I look at the pictures, I think they're really beautiful. I'm struck by the dynamics of it. Things are changing all the time, no matter where you look. And I'm also pretty daunted by the complexity of it all.
That's not surprising. Previous satellites only revealed a portion of the sun in high resolution. Now, they see it in mind-boggling detail.
Now, in order to look at the Solar Dynamics Observatory images that we're bringing in every day, we've built this very special wall, which is 9 high-definition television screens together that can display these images, so that the instrument and the display system together are an entirely new way of looking at the sun.
One of the most important aspects of SDO is its ability to see sunlight across a range of wavelengths, the equivalent of looking at things glowing at different temperatures. Our eyes are most sensitive to sunlight glowing at around 10,000 degrees Fahrenheit. At this temperature, the sun's surface looks almost featureless. But at hotter wavelengths, normally invisible, a far more dynamic picture emerges. The February 15, 2011 storm is a perfect example. In this repeating image, at around 90,000 degrees Fahrenheit, SDO captures just a ghostly trace of the CME wave. But at just over 1,000,000 degrees, the superhot plasma rippling away from the eye of the storm is much clearer. This allows researchers to see coronal mass ejection waves evolving across the entire sun.
This is an absolutely amazing time for solar physics because of these beautiful high-resolution images that allow us to understand better the physics behind what's going on when solar storms erupt.
That one last photo, look at this one.
Back at the National Space Weather Prediction Center,
That's the M1 here.
Bill Murtaugh tracks the storm's CME wave. It carries 1 billion tons of plasma and is now only about 20 hours from Earth.
We're bringing it in mid to late on the 17th into the...
What they see is alarming.
Well, there's actually 3 CMEs that we're looking at. So we bumped up some numbers for late tomorrow. Yeah.
It's not a single CME wave, but 1, 2, 3 of them.
We won't call it the perfect storm yet or anything, but conditions are lining up for some significant space weather.
Their models show trajectory and speed, but the big unknown for Murtaugh is how powerful the waves will be when they hit. The answer lies in a force that governs the sun: magnetism. Earth has a magnetic field that protects us against threats from the sun. But we are less familiar with the sun's magnetic power, which researchers believe plays a major role in driving solar storms. Astronomers know that the surface of the sun spins in a strange way. Travel from the poles of the sun towards its equator, and you'd notice it turns faster. Analyzing sound waves inside the sun reveal that the plasma layers beneath the surface also spin at different speeds. That's because they act like fluid, which gets denser towards the core. The interior of the sun is a place of spectacular turmoil. Turmoil that's the key to the sun's magnetism.
The motions there, the convection, the differential rotation, the motion from equator to pole, are driving a new force. They're driving a magnetic field. There's a dynamo at work here, a dynamo that's generating a force that we actually experience here on the Earth.
It works like a giant wind turbine. Churning plasma in the convection zone stirs up powerful electrical currents, which generate a huge magnetic field.
Have upflows here and downflows coming down this way, right? Those are
The
down
holy
drops just
grail
here.
for scientists is understanding exactly how this dynamo generates solar storms. The clue lies deep within the convection zone. Magnetic field lines normally run from pole to pole. But with all the turmoil in the convection zone, that pattern can't last. Rotating layers stretch them horizontally. Convection twists and braids them. Under immense strain, they begin to kink upwards towards the surface.
Even though the magnetic field lines themselves are invisible, the plasma, which is heated and hot, can light up along these paths. In maybe the same way, you could think of a highway, and at night you wouldn't see the highway at all, but with the cars with their headlights on, you'd see the path of the highway.
Watching field lines is critical to understanding solar storms. As field lines emerge, they form loops. One end has a positive pole and the other a negative pole. Churning plasma beneath the surface twists these loops, pumping them with energy. If twisted enough, positive and negative parts of the loops cross. When they do, they short circuit with a tremendous explosion. The energy released heats the plasma to millions of degrees, resulting in a spectacular solar flare. It's the final dramatic stage of a very long journey. Photons formed in the core make their way to the surface. Some pass directly into space as sunlight. But in the process, that surging energy disturbs the convection zone, generating a magnetic field. The field lines wind up to the point that it explodes in a solar flare. Now, SDO provides a complete and unprecedented picture as these events evolve.
This is beautiful because the hot gas outlines the magnetic field lines that we would otherwise not be able to see. And here you can see even a twisting structure as some of the mass drains back down to the surface, and a lot of it escapes in the eruption. This is the essence of space weather, or solar storms.
This explains how flares form, but it's not the end of the story. Crossing magnetic field lines can cause nets of plasma to be flung into space. This is a coronal mass ejection, a CME wave. The portrait of how solar flares and CME waves form is coming into focus. But a key question remains. CME waves can travel 93 million miles to Earth in a matter of hours. So what gives them such explosive energy? Part of the answer is hidden here in the sun's atmosphere, the corona. It's made of superhot plasma that blisters at over 3 million degrees Fahrenheit. 300 times hotter than the sun's surface. Some scientists suspect that this heat powers massive gusts of energy that blast CME waves toward Earth at incredible speeds. But why the corona is so hot is an enduring mystery.
Understanding it's essential if we want to get to the bottom of how the sun drives space weather and the impact of the sun on the Earth.
The fact that the corona is so much hotter than the surface flies in the face of physics.
The sun's corona is a very odd place. Take this fire, for example. As I put my hands close, sure, it's warm, but as I pull them away, it gets cold. That's not the case on the sun at all. As you go in close, it's definitely warm, but as I pull away, it actually is warmer still.
Recently, Japanese investigators observe high-velocity jets of plasma shooting up from the near surface. McIntosh suspects these jets deliver heat to the corona, but he doesn't have a way to confirm it visually until he turns to SDO for help.
Lo and behold, we actually managed to join the dots and see, yeah, these objects that we could see moving out of the lower atmosphere at high speeds, kind of like these licks of flame, really were reaching a couple of million degrees. It was really a tumultuous moment. We kind of looked at each other and said, wow, what have we just done?
They've shown that the plasma jets accelerating upwards from near the sun's surface generate tremendous heat. As a result, temperatures in the corona soar to 3.5 million degrees. If confirmed, it represents a huge leap forward in understanding CME behavior. The immense heat of the corona acts like a wind in a raging gale. It's constantly pushing on the plasma draped on the field lines, billowing them out like sails pulling on a mast. Like solar flares, when magnetic lines cross, there can be an immense explosion. In this case, the lines are cut and the sail whips off into space. Loaded with 1 billion tons of highly charged plasma, the CME wave can wreak havoc on electricity-dependent Earth. At the National Center for Atmospheric Research, this violent event is captured by satellites.
Now, to see the CME, we need to create a little artificial eclipse. To do that, we block out the light from the disk of the sun, and that's this little circle here. But what that allows us to do is to see this extremely faint, high-speed thing shooting away from the sun. This one moves at about 1,000 kilometers per second.
By enhancing the picture and slowing it down, it's possible to see the shock wave moving at over 2 million miles per hour. Though we have a better understanding of what causes solar storms and how they reach us, there is still a final pressing problem.
Trying to predict when solar storms are going to occur on the sun really requires a lot of detective work. Basically, we're looking for clues and observations to tell us when potential storms might occur.
The best clue comes from these. Sunspots. Dark patches which can linger on the sun's surface for weeks at a time.
A sunspot is a massive region, several times the size of the Earth, which appears on the sun as a dark spot. It's dark because it's relatively cool compared to its surroundings. And it's cool because the magnetic fields are so strong that they're suppressing the flow of heat from below.
The strong magnetic fields which create sunspots are the breeding ground for solar storms. The challenge is trying to decipher a pattern for when and how many will appear.
As we watch sunspots over a period of many years, we see something very interesting. The number of sunspots at any given time will wax and wane over a period of about 11 years. And since we now know that sunspots are associated with strong magnetic fields, this tells us that the sun's magnetic fields are likewise going through a cycle.
The constant churning and twisting inside the sun creates a powerful dynamo, the biggest electrical generator in the solar system. The magnetic field lines it produces get so wound up that roughly every 11 years, the magnetic poles of the sun reverse. After that, calmer magnetic activity prevails and fewer sunspots form, a period called solar minimum. But because of the sun's turbulent nature, the field gradually winds up again. As it does, magnetic outbursts are far more common, a period called solar maximum.
The solar cycle actually determines the personality of the sun. During solar maximum, it can get very angry and it can throw off solar storms that are sometimes directed at the Earth. And during solar minimum, it becomes much more subdued. There aren't as many sunspots, there aren't as many solar storms occurring. The activity cycle basically determines how the sun is going to act.
Prior to the solar storm of February 15th, 2011, things were pretty quiet on the sun. But that outburst marks an ominous turning point. The sun's magnetic activity is winding up again as it heads towards solar max. Just a few days ago, Bill Murtaugh and the team at the Space Weather Prediction Center witnessed the turn.
The arrival of the X2 and the M6, if it comes in with any geoeffectiveness, between 12 and 1800.
So that's what we're seeing here.
It's now time to let the world know what it might expect.
Nothing higher than
In the next couple of minutes here, we're going to have to make a decision and make the prediction that this coronal mass ejection is going to arrive at whatever time tomorrow, and the geomagnetic storm will ensue, of course, once it arrives.
With the event we had...
Murtaugh knows that the severity of the storm depends mainly on two things: how strong the CME's magnetic field is, and at what angle it hits Earth's own magnetic field. CME waves approach Earth like a slowly rotating shield. One end is positively charged, the other negative. With magnetism, opposites attract, and like poles repel. If the wave's positive pole lines up with the Earth's positive pole, most of the power of the storm will be repulsed. But if opposite poles line up, the plasma the waves are carrying will hit with full force.
Did you say it came in at 115?
Murtaugh makes his final assessment only hours before impact.
It could be larger, more complicated, typically, than just your single coronal mass
I
ejection.
think we've nailed the forecast.
Okay. I'd like to think so.
According to the observations, the CME wave will be repelled.
We don't expect it to be too strong. We'll see moderate storming levels, which is good enough to produce some aurora borealis down in the United States, down along the Canadian border, northern tier states, and it will cause some minor problems to the power grid and whatnot.
Space weather for the next 24 hours is expected to be minor. Radio blackouts reaching the R1 level are expected.
This time, we dodged a bullet. But disturbing evidence suggests the Earth will not always be so lucky. It's a cautionary tale. NASA's Jim Green discovered it while researching a book on the American Civil War at the Library of Congress. Green found news accounts from 1859, which caught his eye.
I would run across articles about aurora, fabulous aurora, and this really piqued my interest because it's in my field. It seemed as though the armies of heaven were engaged in terrific, though noiseless, conflict. This terrific aspect soon subsided into a more beautiful and brilliant appearance, a few of which I can only refer to.
The reports tell of auroras so bright, miners in Colorado wake up and go to work thinking it is dawn. Other accounts tell of a more harmful impact on the lone electrical system of the day, the telegraph.
One, for instance, because of the induced current on their system, overheated the battery and started a fire, nearly burnt down the telegraph office. Another operator was burnt so badly he ended up into the hospital.
Green uncovers numerous reports of auroras seen not only across the United States, but around the world. The evidence is clear. Earth was struck by a superstorm in 1859, the result of two massive CME waves.
Those two storms were not only enormous, but they happened one right after the other. No one alive has seen anything like it.
On the day before the waves hit, a British astronomer observes a giant sunspot group light up with two massive flares. The second CME wave hit 18 hours later, allowing Green to calculate its speed, 5 million miles an hour, plowing into Earth at almost 4 times the speed of the February 15, 2011 CME waves. Using the various reports, Green is able to reconstruct the 1859 storm. The accounts suggest that the poles of the CME waves were aligned, and instead of being repulsed, the waves hit with full power. The charged particles funnel down into the atmosphere, electrifying it like a giant neon sign, producing dazzling aurora displays. The storm is so intense, Earth's magnetic field all but collapses. Millions of tons of plasma spill towards the equator, and a powerful electric surge pulses over the globe. For the largely pre-electrified world, the moment passes with minimal damage. That might not be the case today.
It has the potential of knocking out power grids. And if it burns out transformers that are hard to replace, we may be without electricity in many areas for a very long period of time. There's only a few places that make these 125 kilovolt transformers. It takes several months to make them. And if you burn out half of them, we're going to be shooting squirrels and chopping wood out the backyard for a long period of time just to survive.
Everything grows,
building up.
but the 3Ds really brings everything.
Today's solar scientists believe it's not if, but when the next big one will strike. Can we predict when the next solar storm will hit?
Maybe. And the reason why is we've learned so much about the sun. We're getting better at it, but we have a long way to go. And the more we look at some of these historic events, the more we get a deeper appreciation for what we need to know.
Today, we see the sun better than ever before. We're beginning to understand it from the inside out. But its unpredictable personality means there will always be uncertainty when living with a star.
Hidden in the world's iconic monuments is an incredible ancient knowledge of the sun.
This connection with the sun and the sky is actually timeless.
Twice a year, as light breaks across the Earth, their secrets are revealed.
This entire space is engineered around this one moment in time.
Across thousands of years and unrelated civilizations, ancient monuments unite in perfect alignment to the sun. On the same single day, the equinox.
They go and build these fantastic temples, unique in the world, so there must be a driving force.
Each a miracle of engineering and astronomy.
With the technology that they had at the time, it's amazing how much they could have achieved.
But how did the ancient astronomers create this global event? The human race, in a simultaneous celebration of the sun on the equinox. It's 6:15 a.m. in Cambodia. Today is the equinox, an event that happens only twice a year, when day and night are almost the same length all over the world. Southeast Asia waits for the sun. Huge crowds gather at the world-famous temple of Angkor Wat. They've come to witness an ancient but spectacular special effect. The sun is up and rising, just to the east behind the central tower. But the real moment of truth is still to come.
The sun is important in all cultures, particularly in ancient cultures, because the sun is the thing that allows people to survive. Without the sun, there is no survival. It's not a coincidence that it has been deified in ancient cultures throughout the globe.
We still find this connection very deep. Every society that we have studied all over the world and since prehistory seems to have had an interest in the sun, the moon, or the stars.
And on the equinox, our human obsession with the sun is revealed in ancient sites around the world. 2,000 miles to the west, the windows of the Indian temple of Sri Padmanabhaswamy frame the setting sun with exquisite precision. In Egypt, more visual fireworks from the setting sun as it merges into the shoulder of the Sphinx, with the Pyramid of Khafre directly behind. In Europe, the megalithic temples of Manidra predate the pyramids by 1,000 years. Here, too, is a solar phenomenon that occurs only on the equinox. In the Americas, at Chichen Itza in Mexico, dating back 1,000 years, an hour-long light show as a snake in shadow form slithers down the side of the snake god's temple. Peoples from different continents, centuries, and cultures all independently celebrated the sun.
They were keen observers of natural cycles, keen observers of what was happening in the sky. And they built that knowledge into these structures themselves.
When we examine these sites, what we see is not just the skill that these cultures had, but also the importance of time and astronomy and the sun in human life. It's mind-boggling that they had the capability to make these monuments.
In the modern world, it's easy to forget that since the dawn of humanity, every culture on Earth has relied on the sun.
Prehistoric societies, before the invention of writing or farming, were already interested in the sky, and we find evidence for that all over the world.
Astronomy was the first science. Only astronomy makes a reliable calendar possible.
You can't perform agricultural farming practices, you can't sow, you can't plow, unless you know what time in the year it is. They had to know the movement of the sun in order to be able to survive.
In summer, the northern hemisphere tilts towards the sun, and the days are longer. In winter, it's tilted away, and it's cold and dark. But when the seasons change, the sun is directly over the equator, and both halves of the planet face our star equally. Everywhere on Earth, day and night are almost the same length, 12 hours.
The word equinox comes from the Latin equinoctium, which encapsulates the idea that the night has the same length as the day.
You come out of the darkness of the winter, and your days now, from the equinox onwards, start to grow and become longer, because light brings life. The equinox is the reaffirmation that the world is waking up, the cosmos is waking up again, the earth is waking up again, and your survival can carry on.
Ancient civilizations developed the astronomical knowledge to plot the sun's movements with precision, and then the engineering skills to celebrate those movements in stone. The mystery is, how did they do it? For archaeologist Dr. Sarah Klassen, the alignment with the sun at the equinox is one of the most spectacular features of the temple at Angkor Wat. Sarah is using new technology to discover the secrets of ancient structures.
This is a total station, and we use it in the field to collect very high precision geographical locations for points of interest. So we can use it for architecture, like here at Angkor Wat, and we can then load into a computer to understand how the temple was built, what angles, what the different lengths are between the different features.
The Temple of Angkor Wat was built 800 years ago by Emperor Suryavarman II and stood at the heart of his empire,
We can tell that the ancient Khmer were extremely sophisticated when it came to their engineering, both in terms of the scale and the precision of the types of things that they engineered.
It's on the equinox that this sophistication becomes clear. Angkor is aligned towards the rising equinox sun. One set of grid lines runs north to south. The others run west to east, into the rising equinox sun. From the western gate, a dead straight avenue leads directly to the heart of the temple. But modern measurements reveal that the alignment is not quite due east.
The one thing that's really unusual about Angkor is it's not built exactly on the cardinal directions. It's actually half a degree off.
For these ancient masters of geometry, half a degree would be a huge margin of error. But in fact, it's no mistake. It's a deliberate stroke of mathematical genius.
It's actually quite ingenious. We think they did this so that during the equinox, the sun would rise directly over that central temple.
The trick is that the equinox sun rises at due east. But in the minutes it takes to rise to the height of the tower, it also moves right across the sky, half a degree off due east. If the tower was due east, the sun would be out of line when it reached the top. So the architect's solution was simple. They rotated the entire layout to compensate by exactly half a degree.
To create an alignment between the western gate, the top of the tower, and the sun on the day of the equinox is a huge amount of skill.
8 centuries later, it's still a calculated mathematical miracle. One that proves the equinox was a vital moment for which the entire temple was constructed.
The beauty of Angkor Wat is in the mathematics of it. It looks and feels like everything was minutely planned and detailed to a mathematical level of precision.
After working here for over 5 years, it's really exciting to kind of finally be here for this moment that this entire structure was built around. The energy of the crowd, all the excitement of everyone being here, it's a very special moment.
A fraction, half a degree, makes all the difference.
To actually capture the sun right at the top of the central tower of Angkor Wat. They were using the sun to make a statement about their own beliefs, and in this case, their own power and their place in the cosmos.
The temples that we see today are not what the temple would have looked like in the past. The temple may have been coated entirely in gold, so you can imagine what it would look like with the sun rising over the central tower. A powerful moment to experience.
The emperor's architects had got it right, to the last tiny detail. Angkor Wat is one of the world's greatest ancient sites, but just one of many across the earth that celebrate the equinox sun with a spectacular light show. As the equinox sun leaves Cambodia, it continues its journey around the globe. In Kerala, 2,000 miles to the west on the south coast of India, the crowds have to wait for sunset to witness the effect. The stunning temple of Sri Padmanabha Swami has a beautifully carved tower dated 400 years after Angkor Wat. Through its series of precisely aligned windows, the equinox sun sinks into the west like an elevator, lighting up stories at 5-minute intervals. Another quarter of the way around the world, in ancient Egypt, the setting equinox sun hits two of the most iconic structures on Earth. The Great Sphinx of Giza and the Pyramid of Khafre are both believed to have been built 4,500 years ago. On the equinox, the setting sun merges into the Sphinx's shoulder, with the Pyramid of Khafre behind. The alignment of all the Giza pyramids to the setting sun in the west is incredibly accurate, within 1/15th of a degree. The ancients may have achieved this using the simplest of tools.
One possible way of orienting structures to the points of the compass is using the Indian circle method. This method consists of an upright pole and observing the shadow that is cast by the sun between sunrise and sunset. And you would mark the movement of this shadow on the ground. Then you would take a rope of the same length as the wooden pole that you used, and you would tie it around the pole and draw this circle on the ground. This intersect at 2 points, and if you draw a line between these 2 points, you've got a line that is marking the east-west direction. When you look at it from above, it does seem to fit perfectly with the points of the compass. This method is so simple and so powerful, so accurate, that it could actually be used by any society anywhere in the world.
On the day of the equinox, the sun's journey continues onwards onto Europe, bathing the Mediterranean in light. On the island of Malta, something incredible is happening. The rays of dawn penetrate a prehistoric temple 1,000 years older than the pyramids, with breathtaking precision, striking the center of the ancient altar dead on.
They were specifically targeting the equinox. Pinpointing the exact position of sunrise at the equinox is incredibly difficult, and that makes it even more amazing that some societies did manage to do that.
It's a miracle of astronomy and architecture, made 5,500 years ago.
The people in Malta were building these fantastic, great, massive structures, and building so many of them on such a small archipelago that this is unheard of anywhere else in the world.
The temple at Manidra is one of the oldest temples in the world. Built with stones weighing 30 tons each, the equivalent of 5 elephants.
They clearly were not that primitive. They clearly had the skills, the ability, the know-how. It's fantastic to think that this was built to align with the equinox.
For the last 10 years, archaeoastronomer Tore Lomsdalen has been focused on figuring out exactly how they did it.
Every time I come here, I'm amazed and I think about the knowledge they must have. They go and build these fantastic temples, unique in the world, so there must be a driving force.
There are 3 separate temples at Manidra, arranged in a cloverleaf shape. They're aligned in different directions, with one facing east to the equinox dawn.
They knew what was going on in the sky. They oriented towards the eastern horizon to be able to observe how the sun moved through a solar year.
As well as the days getting longer and shorter through the year, the precise spot on the horizon where the sun rises also moves. In December, it rises at its most southerly point. At midsummer, it reaches the furthest north. The equinox sunrise at due east will be right in the middle of the two extremes.
That middle point would be close enough to the equinox for them to build a structure that was aligned to it.
Torrey believes the temple builders use this method to keep track of the sun throughout the year. That Menidra was a calendar built in stone. A tantalizing clue lies at the winter solstice position.
This hole could have been a marker for the builders when they built the Nidra to align to the rising sun at the winter solstice. It's so perfectly aligned.
There may have been a similar marker for the equinox, but this method isn't very accurate, especially on a steeply sloping clifftop like Menidra. By the time the sun is high enough to see, it already has drifted to one side.
You are going to be finding a point that isn't exactly due east. It's going to be slightly to the left or slightly to the right of east, which builds in this error into the method.
This method was likely only used for the design of the first temple, believed to be a single chamber facing the horizon. The equinox sun would have entered the temple at a slanting angle to hit the altar at one side, rather than dead on. But over time, the temple was rebuilt with new astronomical knowledge.
There was an evolution in their astronomical knowledge and development of how they wanted to have the temple oriented directly towards the equinox sunrise.
And surprisingly, that new knowledge may have come at night. In Malta, the ancient astronomers needed a new method to align their temple precisely to the rising equinox sun. The answer, it seems, lay in the stars.
They were using particular stars that rise at the exact location as the sun rises at the equinox, as very accurate markers for this event.
Astronomers believe they use these pillars to mark their observations. There's a cluster of holes that's thought to represent the stars in the Pleiades constellation, also known as the Seven Sisters. They're bright and prominent in the night sky. By chance, the Pleiades rise at due east, the same place as the equinox sun. But while the sunrise moves along the horizon, the stars come up in the same place every night, because they're 30 million times further away than the sun.
Almost every night of the year, you just spot where the Pleiades are rising, and you will know the sun will rise at that exact spot on the days of the equinox.
The showpiece of the new temple would be the huge central altar to catch the rising equinox sun.
They developed more awareness, and this whole temple was built to center around the equinox.
It took more than 1,000 years to reach the final design. The altar was at the back of a completely new chamber, so deep into the temple, the sun could never fully reach it, except on the equinox. Prehistoric humans sent a message we can still read today.
The brightness, look how beautiful.
The equinox sun still comes right down the central corridor to bathe the altarpiece in light.
Look at the passage. How the sun is increasing. It's going to be 100% today.
Whoa.
The light hits its target with extraordinary precision.
At the equinox, this corridor has just the right length to create this effect where the sunlight just hits the bottom of this altar in the back. It's fantastic that this was an intentional alignment.
Some of the first builders built for the equinox.
5,000 years ago, they made these temples. This is absolutely the oldest, and it's amazing.
Just 1 hour after Malta, the equinox sun reaches across Europe to rise on Stone Age Ireland. 1,500 miles from Malta, the same effect. The dawn light hits ancient stone at the back of a chamber, and a carved symbol of the sun. This is Loughcrew in County Meath, a Stone Age site like Malta and almost as old, dating back 5,000 years. A farming society was greeting the arrival of spring.
They were building those relationships they had to the cosmos into the structures that they were building or into the art that they were painting.
The light descends to a second carved image of the sun. Prehistoric people marking the equinox as a matter of life and death.
What you are basically doing is ensuring that the sun will shine or will do what it's supposed to do in order for your crops to grow. You're addressing the cosmos in order to be able to ensure your own existence and your own survival.
The equinox leaves Europe far behind. The dawn light races across the Atlantic Ocean and finally hits America. In northwestern New Mexico, the sun climbs ever higher over endless desert. Archaeoastronomer Anna Sofer has been drawn to the Pueblo ruins of Chaco Canyon for more than 40 years.
I am stunned by the beauty of Pueblo Bonito. It is so gorgeous. Look at just those doorways and the perfect right angles to the edges. Look at the way it's held up for so long. Isn't that incredible? That people built this 1,000 years ago?
This is ancient territory spanning more than 30,000 square miles of the American Southwest. In the early 12th century, these were the lands of the ancestral Puebloan people, one of the most sophisticated civilizations of the ancient Southwest, who believed they'd been led here from the north, the spiritual home of their ancestors. The ancestral Puebloans reshaped the canyon with hundreds of structures that seemed to grow organically from the rock. And their obsession with the equinox led them to construct one of the greatest single buildings of ancient America, the iconic Pueblo Bonito. In the brutal high desert landscape of New Mexico, archaeoastronomer Anna Sofer explores a mysterious ancient structure. This is Pueblo Bonito, one of the biggest single buildings in ancient North America, built in a place too barren to support the numbers who could live here.
This room shows you how large the interior rooms of Bonito were. We're standing on the top of the first story, and we are in the second story. And then above those vigas, those wood posts, you see the third story, and you get a little look at what was the fourth story. So it's a massive building.
The sheer scale sparks the greatest mystery of Pueblo Bonito. Thousands came, but very few stayed to live.
It's really difficult to think of people living here. If you imagine 2 stories above you, you're enclosed. You cannot have a fire, you can't have a hearth. It's a great puzzle. What were they doing? what we're looking at is a site that was built for religious purposes, for very powerful beliefs, and those beliefs are based on relationship with the cosmos.
They came to Chaco Canyon to worship the sun. Paul Pino is an elder of the Laguna Pueblo, a modern community directly descended from the original Puebloans.
The culture that created Bonito, that culture is not gone. It continues today in the pueblos here in New Mexico. My grandchildren are part of that culture, living every single day. They're a part of it, and they will pass that on to their children.
Cameras are not permitted inside Pueblo ceremonies, but in this rare footage, worshipers are leaving a kiva, a circular underground structure where rituals and meetings are held.
I believe that when the people lived here, they performed a lot of their ceremonies, much the same as the ceremonies that we do today. There's that continuity from the past to the present.
Pueblo Bonito alone has 36 kivas, with room for up to 50 people in each. The Puebloans saw order in the way the sun moved and mapped it onto Pueblo Bonito. On the equinox, the sun rises in the east at the end of the enclosing wall. Sunset happens in the west at the other end of the enclosing wall.
This wall, that's the exterior wall of the building on the south side, is so exactly east-west that on the nights of equinox, you can view the sun setting on the trajectory of this wall.
And Pueblo Bonito is only the largest building in an entire ritual landscape. The whole canyon marks the equinox. There are 14 great kivas, like Casa Rinconada. The giant circles could each take 400 people, almost 6,000 in all.
The kiva is so important in the ancient Chaco culture. This is the ceremonial site for most of their activities that were related to the sun.
The kiva had a heavy earthen roof. In the dark interior, worshippers would only see the sun through the niches in the walls.
It was organized to the cardinal directions, north, south, east, west. Over there, the north side of the building has a rectangular structure with two doorways that are aligned to the rising of the equinox sun.
Everything is aligned to the compass within a few degrees. The doorways of this rectangular structure open east and west, so the rising equinox sunrise shines through both and floods the interior with light. 2 days a year until the end of time.
The sky and the earth were created at the same time. In our belief, the sun was created to give light to the world. So the sun and the earth work together to provide nourishment for the people.
The equinox sun bursts into kivas across the canyon.
It must have been, at its height, something phenomenal to see.
What we are exploring are sites where people were gathering in order to have this experience of space, but also this connection with the cosmos.
The alignments represent a particular order in how things are done. And sometimes in this modern age, that order is missing, and we mess up our world.
The Pueblo marked the equinox with one final spectacular display. This is Fajada Butte, a sacred overlook where most likely only the elite astronomers of their civilization could ever go. On its side, Anna found 3 sandstone slabs, appearing to be set by hand against the rock face. There was a spiral pattern carved into the rock. She was just in time to watch a dagger of sunlight appear from nowhere.
The precision of that within a few minutes of noon, I think it's 4 minutes of solar noon.
On the west face, another spiral pattern, this time a double.
It has a dagger of light going up through the right lobe. Again, noon equinox.
What makes Chaco Canyon unique with respect to the equinox is that it shifts the emphasis from the sunrise or the sunset and puts it at noon.
It's like clockwork. It's like all of that is happening at once. The sun dagger site marks equinox. These two sites mark equinox noon. It's the same that we see in the buildings, the same people, the same mindset to align themselves to the sun, the power of the sun.
1,500 miles from Chaco, the Maya built structures that dwarfed even Pueblo Bonito. And they created the greatest solar effect of all, the climax of the sun's entire journey. In the ancient city of Chichen Itza, in Mexico, thousands of people have gathered from far and near. In a few hours' time at this ancient pyramid, they will witness quite possibly the single most spectacular effect ever created with the equinox sun.
This is not your average alignment to sunrise or sunset. This is a complicated 3D effect that involves the light of the sun hours before it sets to construct this dynamic shadow play that is uniquely Mayan.
1,000 years ago, the vast Maya Empire was centered here, in Mexico's Yucatan Peninsula. But their civilization was already 3,000 years old. It has become a byword for sophisticated learning, astronomical knowledge, and above all, stunning buildings. This is called El Caracol, Spanish for the snail, because of its distinctive shape.
It has this dome shape at the top. When you look at it from our modern Western perspective, it looks just like an observatory. So maybe people were sitting there inside this structure looking for the sun or the moon or the planets.
For site director Marco Antonio Santos Ramirez, El Caracol was of central importance to the Maya.
Los astrónomos se la pasaban aquí todo el tiempo y eran atendidos por muchas gentes porque ellos eran los especialistas. Por siglos y siglos, ¿no? Hubo un registro en torno a los fenómenos astronómicos.
Astronomical observations and knowledge was restricted to a specific elites, for example. And by doing that, what the Mayans achieved to do is maintain power. So your power was maintained through the knowledge of how the sky operated.
By the time Chichen Itza was built, Maya astronomers already knew exactly how the sun, moon, and planets would move. El Caracol is not so much an observatory as a calendar made in stone. The slits in the walls were deliberately placed to record the passing of the sun on certain vital days. A pair of slits records a specific sunset on the equinox or the solstice.
Estos alineamientos servían precisamente para establecer en qué momento del año se encontraban.
Marco's colleagues have been capturing the effects throughout the year, reconstructing the detailed knowledge base that the Maya had built up over centuries.
Ver cómo el sol entraba en estas puertas, ¿no? Para registrar, ¿no? Estas líneas de luz que marcan precisamente los momentos específicos que están ellos queriendo registrar, ¿no? Parece algo muy simple, porque pues, es una línea de luz, pero para llegar a esto hay un conocimiento ancestral de muchas generaciones.
The Maya knew the equinox was vital for the survival of crops.
En el caso del equinoccio, Era un momento simbólico importante porque, es decir, la temporada de secas es la temporada de muerte y la temporada de lluvia la temporada de vida. Y posiblemente esté marcando, ¿no?, el inicio de una y el término de la otra.
To guarantee their survival, the Maya believed the gods had to be placated at the equinox. And at Chichen Itza, one of the most powerful gods was Kukulkan, a winged serpent who flew ahead of the rain god Chak, bringing in the wet season, as his tail moved the wind and swept the earth clean. The Maya built their pyramid in his name and carved his image into its facade.
Kukulkan es un dios creador del tiempo, del universo, del hombre, del maíz, del fuego. Es como un renacer, ¿no? Una lucha entre estas dos fuerzas, la vida y la muerte.
At the equinox, Kukulkan would be celebrated with a spectacular light show. On the day of the equinox, tourists at Chichen Itza wait for the spectacular moment that marks the arrival of the new season. It's now just minutes away, and tension is rising. Clouds threaten to ruin the crucial moment. The crowd prays they'll see the true extent of Maya religious power.
To create this effect is very complicated. And yet, they've done this almost 1,000 years ago without any of modern mathematics or computer technology.
Todas las personas están alrededor de la pirámide de Kukulkan esperando ese momento.
The pyramid's key feature is this sloping edge on the northwest corner. Each of the steps protrudes a little in a triangle-shaped bump. The Maya realized that these would cast shadows on the nearby staircase, and they could use them to conjure their illusion.
Bueno, aquí es donde se va a poder observar cómo se forman los triángulos de luz y sombra.
The whole effect will happen in 3 dimensions. The sun is moving in a curve across the sky. The edge is sloping down and sideways, and the staircase is a flat plane at a different angle. So the Maya architects had to solve a highly complex problem.
This must have required amazing skills. What they must have done is create a small-scale 3D model made of maybe wood or clay, and actually go out there and use the actual light of the sun on the day of the equinox to cast light on this model and play with it until they found exactly the effect they were looking for.
The basic shadow is a line of triangles, but if the Maya changed the shape of the sloping edge, it would change the shape of the shadow. They could use their model to get the effect they wanted. The equinox moment is almost here.
Conforme el sol va descendiendo hacia el oeste, poco a poco se van a ir formando los triángulos de luz y sombra.
We cannot be certain what effect it must have had on the watching Maya people. It must have been part wonder, part terror.
En este momento se está empezando a formar precisamente.
Kukulkan himself had appeared on the face of the earth. It's not the shadows that count, but the light. The brilliant outline of a serpent's body slithering down the staircase to join his head at the base.
Viene a ver esto, el descenso de Kukulkan y cómo fertiliza a la madre tierra.
For the Maya, this was the ultimate expression of the equinox. Kukulkan had descended to Earth to banish the dry season and bring rain and new life.
Lo maravilloso que es el que el conocimiento ancestral se pueda seguir viendo.
In modern society, we have lost touch with the environment that's around us, and that includes the sky. But in particular, we've lost touch with the equinoxes, which would be the true moments of transition between the warm half of the year and the cold half of the year.
Leaving Mexico, the sun passes over the Pacific Ocean and finishes its equinox journey. Civilizations long forgotten, unknown to one another, celebrated this day. For the ancients, the sun was the giver of life. First, they needed to understand its journey. Then they wanted to harness its power, developing the first knowledge of astronomy and engineering to do it. Chasing the equinox, the ancient astronomers created a cosmic magic.